Today we're speaking with Geir Kjosavik, product director at Nordic Semiconductor. How are you doing, Geir? How are you doing today?
Hey, doing fine. Great. How are you?
I'm doing well. I'm doing well. And we're talking about Nordic Semiconductor's power management ICs, right? And the power management sort of business strategy. And maybe I could just kind of jump right in here. There's so Nordic Semiconductor, they dominate, right, in BLE, right, Bluetooth low energy, and from what I understand, there's 4 distinct business units, and so there's the short range wireless, there's Wi-Fi, long range cellular IoT, and then PMICs, right? So power
Yeah,
management ICs,
correct.
and that's a divergence from the wireless space. So as primarily a wireless company, what inspired the move into power management ICs?
Yeah, that's a good question. So the obvious answer is that with a, what is it, 40% market share in
Yeah,
Bluetooth,
yeah,
any growth from there is gonna be very resource demanding. So Nordic is looking for more ways to put more content on customers' PCB to increase their footprint.
mm,
But that is just one part of the story. The more important thing, I think, in this is that Nordic, being a leader in low power wireless IoT, they want to be an end-to-end solution provider for the reason that when you make low power wireless IoT products, you need to think about energy preservation all the way from the battery to the antenna.
yeah,
The energy that you are transmitting as radio waves is going to come from somewhere, and that
mm,
whole energy path needs to be as efficient as possible.
yeah.
And now you can hook our cloud services to that, and it's like we're now we owning the whole game here, all the way from the battery to the antenna and onto the cloud.
Yeah, right. There was that Memfault acquisition too, so that was the path towards the
Exactly.
cloud.
Yes.
Um, what is there a strategy kind of behind the PMIC business? Because is it intended as a companion to the wireless SoCs really? Is that or are they more, or is that business become more standalone? What's sort of the plan there for Nordic Semiconductor?
Yeah, the plan is twofold. Obviously, the low-hanging fruit is to piggyback onto our wireless SoC sales.
Mm,
We have an established customer base. We have
yeah,
great relationships with our customers that our salespeople can leverage. So the going in there and offer a PMIC in addition to the SoC, which is already being discussed, that is a great way to get started. And we're seeing that. The attach rate to our SoCs is on a steady upwards trajectory. But
mm,
going beyond that, obviously it is a goal of ours to also move outside of our established customer base and those who are using our wireless SoCs. And we already do have customers where the Nordic PMIC is the only Nordic component on the board. Now, I just only expect that to be growing as we
mm,
go along. So we have this short, to summarize, great start, great catapult with just piggybacking onto the SoC sales.
right.
But the growth on the long run is going to be along 2 vectors, both alongside an SoC or alongside somebody else's wireless SoC, or maybe a non-wireless MCU for that matter.
Yeah, that I wanted to ask a little bit more about that. Maybe kind of the benefits of Nordic as a standalone PMIC, because the market is quite large and established there. I know that Nordic's power management ICs or PMICs, right now they've got something called fuel gauging,
Mhm.
and that's a sort of a competitive uh, advantage potentially. So maybe you could talk a little bit more about the thought process behind fuel gauging and the benefits there.
Yes. So the fuel gauging is a, let me phrase it this way. So customers have gotten a lot more picky with fuel gauging over the years. And as manufacturers of electronics pushing the boundaries of what a battery powered product can do. Having very precise control over how much energy is left in the battery becomes crucial. But fuel gauging up till now has kind of been a choice between one solution that is expensive, power hungry, and accurate, and one that is cheap, uses no power, but is grossly inaccurate. So the investment in achieving the precision that customers have been gotten to expect has become very, very large, both in terms of bill of materials, physical space, and also power consumption. The ironic thing is that, especially for small batteries, now we can talk about smart rings and really small things, because this gets worse with smaller batteries, is that you can get very precise fuel gauging by significantly shortening the time between charging, which is really ironic. So it's kind of, you have to pick one of two evils here, and it really is a difficult choice to make for designers. So what we wanted to do is to take the best of both worlds here, to try to give somebody the precision that dedicated hardware solutions provide at the cost and the power consumption of the lookup table, which we've almost succeeded 100%. Obviously, our power consumption is going to be a little higher than the lookup table, but it's even for small battery applications fairly insignificant.
And actually, you talked about the lookup table, and my knowledge here is limited. So but from what I understand, there's a lookup table. Let me just look at my notes here, right? And there's Coulomb counting or voltage-based lookup table in order to ascertain the usable energy left in a battery.
Yes.
So how does the Nordic's fuel gauging model kind of differ from that?
Right.
Yeah.
The Coulomb counter, which is the dedicated hardware solution that I talk about, this is the expensive, power hungry, but very precise way of estimating the amount of energy you have left. That is a chip that measures the energy flowing into and out of the battery very precisely. Hence, Coulomb counting. Coulomb is the SI unit for energy.
Yeah.
So that is where that name comes from. It does that really well. It had some of these solutions come with some drift issues that have to be compensated for, which is a nuisance, but they mostly are the established way of doing this. But it is an extra chip, it is extra hardware, it's going to cost you money, it's going to cost you power consumption. The lookup table, what it is that you take the discharge curve of the battery, you just reverse engineer it, and you make a lookup table saying that, okay, at this voltage probably means that I have this amount of energy left in the battery. And the only thing you do is that you measure the voltage of the battery, and then you put that into a table that gives you an estimate back on the percent of state of charge that the battery has. The problem is that there's so many things affecting that measurement, such as the current consumption at the time of measurement, the temperature of the battery, and some other factors as well.
So from what I understand, the fuel gauge algorithm that Nordic uses, it runs on the host processor rather on the PMIC itself, right?
Yes, just as the lookup table is an algorithm that runs on the host processor. But that is the only way to get rid of the extra, the costly and power hungry hardware, is to absorb that into an algorithm. But the algorithm is a lot more sophisticated than the simple lookup table, because what it does is that it looks at battery temperature, battery voltage, and battery current. So it takes three vital parameters as input, runs that through some digital filtering wizardry, and very accurately estimates the state of charge based on that. And the accuracy or the precision achieved is completely comparable to a Coulomb-counter solution.
I am kind of curious, because that is as you're saying, battery accuracy, like very accurate battery monitoring. I mean, there's got to be applications potentially beyond IoT? And obviously it's very important for IoT because
Yes.
you have these devices that have to last for say 2 to 3 years to almost 10 years without maintenance. Have you seen applications beyond that? If so, what are they?
Well, there's two. So you're saying applications that need to last for 10 to 12 years. Yeah, that would obviously be primary cell applications, where we also offer a fuel gauge solution. The primary cell primary cells fuel Coulomb counting is usually not an alternative because, as you say, with a very limited energy budget and up to 10 to 15 years, to achieve 10 to 15 years, your application has to be sleeping for a large amount of time. Typically, a sensor that lasts 10 to 15 years only wakes up every hour maybe to do a short measurement and transmit data and then goes back to sleep. So it spends most of its time in sleep. And Coulomb counters have this disadvantage that they have to also be active when the application is sleeping, because it needs to also count the coulombs that are lost with the sleep current. Our solution does not need that. It has some background information on what the typical sleep current is, and when it wakes up, it can correlate that with what it sees has gone on with the battery and can very precisely estimate how much energy was lost during sleep, even if it did not take a single measurement during that sleep period. So our power consumption in sleep is exactly zero because we don't wake up the SoC to do any measurements until it wakes up to do other things that it has to do.
It's very interesting. I know that Nordic's first PMIC was launched in 2021, right?
Yeah, correct.
And so there's 3 PMICs for rechargeable batteries, and then one primarily for one for primary cells or non-rechargeable.
Yeah.
How does charging and monitoring change for primary cell IoT devices versus those rechargeable battery use cases?
Yeah, the use cases are similar and they're different. Where they kind of have a common ground is that preserving energy is important. For primary cells. It's to maximize the time between charging, or to go with a physically as small battery as possible. That same thing applies to primary cell products. There's no recharging, but there's a time between battery swaps that the people want to extend as far as possible. So what I talked about, preserving that precious energy that is in the battery by being as power efficient as possible is the same requirement for both. Now, how they achieve that is a little bit different. Primary cells have a very wide voltage range. If you run something off of a single AA or AAA cell, the cell will typically start out at about 1.6 volts, 1.5, and then it will run all the way down to 0.7. That's the point where you should stop using it because they start venting, spilling their guts, so to say. But at 0.7 volts, the battery or 0.8 volts before it dies, it can still deliver power, but the voltage is so much lower than whatever is running inside the circuit. So you need a boost converter to boost the voltage. Whereas on rechargeable products, you have a nominal, you often start out at 100% at by maybe 4.2 volts, 4.4, and then you run down to 3. So if you're running a 1.8 volt circuit, you're always under the battery voltage, and you can go ahead and use a buck converter instead. And then is the case with primary cell products is that, yes, they do not have the luxury of being recharged. So, for example, ship mode, if you're going to ship the product with a factory installed product, or you're going to go to sleep for long periods, you need to have very, very low sleep currents to maximize the battery life, because you can't compensate by just shortening the charge cycles. Somebody has to physically change the battery of the application, and many for many single, for primary cell applications, the whole battery change is an expensive operation for a remote sensor, for example, where a service person has to go out and change the battery.
Mm.
Yeah.
Thank you. I was thinking maybe we could, sort of pivot a little bit, and what we talk about. We could talk about how Nordic started in the PMIC business. I understand, like, we chatted a while back, and I remember you mentioned that, Nordic wanted to kind of get their analog IC, sort of their power management designers out of the node that they were working, which was just not very efficient for power management. And I know that the Nordic's SoCs are moving down towards 22 nanometer, and the PMICs are on a 180 nanometer process. Can we talk about that a little bit more? The history of that. And maybe we could talk about the design freedoms that the engineers gained by moving to a dedicated 108 nanometer process that they couldn't achieve on the SoC node before.
Sure. So if we'd had a chip designer in here, we could probably talk about how more efficient transistors are and all those kind of things. That I don't know. I just know from what they say is that achieving high efficiency on, for example, a DC-DC converter in 100 nanometers is easier than, you will achieve higher efficiency than you do at 22 nanometers, even with the best designers on the job. We've done benchmarks between the buck converters that are on our dedicated PMICs versus the ones that come on our SoCs. And even though they're designed by equally skilled engineers, there's a profound difference in the efficiency that you see. And that's just laws of physics that are at play. But there are also other factors in this. As we get into 22 nanometers, and we see this on our 54 series, we do an excellent job of managing the higher leakage currents because now the gate oxide material is so much thinner, you get a lot of tunneling, and you need to be managing that leakage current, which is a static background current that is just, I think, goes up with the square of your supply voltage. That has to be managed really, really carefully, and a lot of the design resources go into actually doing that. We couldn't do that on a PMIC. The PMIC is connected to, if the PMIC is connected to a 4.2 volt battery, the leakage is going to be horrible in sleep mode, and there's nothing we can do about it because we have to be connected to that battery. So that is one thing. Then it's I think the way that the buck converters turn out more efficiently is also because these processors are made for analog. The design catalog for 160 nanometers comes with really robust analog products that comprises really robust analog building blocks that we've designed that are so much easier to handle because there is a lot. We're going into a process that was really tuned for mixed signal design. Whereas the 22 nanometer process is made for high density digital only. So there's a lot of tweaking to make good analog stuff out of a process that wasn't really made for it. And then there is another really important feature. So if we made an PMIC in 22 nanometers, it would be a little smaller because the digital electronics would shrink to almost zero. It's so much more efficient, right? But the analog electronics would not scale at all. Because here, if you're going to make a transistor with a certain on resistance, it'll take up exactly the same area in 22 nanometers as it does in 180. But the process is so much more expensive. So whatever you gain in shrinking the device because the digital part gets much smaller, you get back multiple times in a much higher wafer price. And and just don't get me started on the difference between just the mask cost of 22 nanometers versus 180. It's just
So is it entirely practical? Get the PMIC
it
team
is
out, let
not
them do
very
their own
practical.
thing, and yeah,
Yes, yeah. So
yeah,
they're yeah, and this and we also, I think, it talked about this is going to get to a point where it becomes impractical also, as doing what we do today that we do really well, but we can see us lagging a little bit in terms of performance versus the 180 nanometers and the dedicated PMICs. That gap in performance is just going to increase as we move along.
Yeah, yeah, and speaking of that, like this gap in performance, and since the PMIC business, it's its own business unit at this point, right? What's on the roadmap there? Is, I don't know, is 130 nanometers on the roadmap? More functions, more capabilities. What? I mean, obviously, there's going to be things that you can't talk about, but I am curious to know what's next.
Yeah. So I can't discuss any concrete plans on that, but what I can say is we're always considering the optimum balance between performance, manufacturing cost, and development time. And 130 nanometers obviously is a part of that ongoing consideration. It would be foolish for us to be just stuck on 180 nanometers and not be looking at the alternatives. And there's also, even though the investment in these more coarse process nodes is not at the same scale as the finer one, where it's kind of a race to the bottom that's going on all the time to just cram more and more and more transistors onto one chip, there's some development going on there that we can benefit from. So what we're looking, the alternatives that we have today may be different from the ones that we have a couple of years down the road. So we're always looking for this.
That was my last question. So is there any sort of last comments, final thoughts that you wanted to share?
Yeah, no, I want to say is that our fuel gauge is really important selling feature for us, as is the whole PMIC. Our tagline is, what is it? Oh, geez, I should know. It just dropped out of my head here.
Don't worry, I can always put it in the caption underneath.
Integrated, flexible, and easy to use. Yes.
Integrated, flexible,
And
and easy to use. Okay.
the integrated thing, that's incorporating a bunch of system power management features that you don't see on most PMICs, and fuel gauge being a very important thing. So that makes it rather disruptive. Now we launched the 1304, which is low charge current version of the 1300 back, I think it was last year. And it is now targeting the smaller batteries. That is what we're seeing, that there's a new class of really miniature devices with batteries down to 5 milliamp hours and all of these things coming out. Smart rings being one example, but also other microscopic products. Okay. And that is what I talked about, this race to the next process nodes, cramming even more and more processing power into impossible small spaces.
Yeah.
That is enabling a new class of devices, smart glasses, for example.
Yeah.
I mean, 5 years ago, who would think that you would have a pair of glasses with two 133 megahertz 32-bit processors in them, one on each stem? No, you wouldn't think that was right, but these things are happening, and these things need impossibly small batteries, and they go into impossible small spaces.
Small form factors, yeah.
Yes, and there is a PMIC that you're going to see announced from us sometime towards the end of this year that is targeting those spaces, and it's going to be an awesome product.
Well, that is exciting. Thank you so much for sharing all this information. I really appreciate your time. No more questions. So you're off the hook.
All right.
Thank you.
Hey, thanks. That was fun.